Thank you. So I want to tell you all today a little bit about lattice gauge theories, which, as we will see, turn out to be models of probability theory. And then I hope I can convey some of the basic intuition about how these random systems behave, and also try to give an idea of some of the basic questions one can try to ask and answer about these models. Yeah, and so I want to start this talk by saying a little bit about where these lattice gauge theories come from and why we study them. Yeah, so it turns out that they're discretizations of these things called Yang-Mills theories. And these Yang-Mills theories are supposed to describe the standard model of physics. Apparently, the standard model is perhaps one of the most fundamental theories of nature that we have at the moment. And so, to maybe draw an analogy with some more familiar objects, I will say that lattice gauge theories are to Yang-Mills theories as random walk is to Brownian motion. So if you recall, Brownian motion is supposed to be this random continuous function defined on, say, the unit interval 0, 1. And if I discretize this interval, what I get is exactly a random walk. And so entirely analogously, these Yang-Mills theories, which I won't really go into today, but I'll just say that they're supposed to be models of random functions defined on continuous space. So say RD for some D, or more generally some manifold. And if you discretize your space by a lattice, what you get is exactly a lattice gauge theory. And so that's how they arise. And you might be wondering, okay, so why do we discretize? Why not just work in the continuum? Well, it's a general fact or general advantage of these lattice models in that they are perfectly well-defined and easy to construct just directly. So again, just think random walk. I can construct it or define it in a couple sentences, right? So I start at 0. At each step, I flip a fair coin. If it's heads, I go up. If it's tails, I go down. So that's how one would construct the random walk. So in contrast, Brownian motion is a bit harder to construct, right? If you want a random continuous function satisfying certain distributional properties, it's not entirely elementary to actually construct such a thing. And so the same thing with Yang-Mills theories, it's a bit harder to construct them. And in fact, a satisfactory construction has not been given, except for in special cases. So that's sort of why we study these lattice models, because we sort of want to study these physical models, but at least in the continuum, we don't have access to them because they're not constructed yet. And so we go to a lattice. So that's one of the reasons. I guess another reason is also these lattice models turn out to be very mathematically rich. For example, we study random walk, even though we have Brownian motion. And yeah, so that's one thing. So at the end of the talk, after this talk, you would like to learn more about lattice gauge theories, Yang-Mills theories, and how they all relate to probability theory, I would encourage you to take a look at this survey by Chatterjee titled Yang-Mills and Probabilists. Okay, so that's sort of some motivation for why we study these lattice gauge theories. And so now on this next slide, I will just to prove to you that they're not so hard to construct, I'll give you a definition on this slide. So to start, we have this parameter G, which is usually taken to be some subgroup of the unitary group. So for some capital N, usually in physics, you would take G to be a compact Lie group. So perhaps the most important example is if G is SU3. But mathematically, you could also take G to just be a finite subgroup of UN, as I will later do. And so the identity of this group is, I'll just denote I sub n, just the n by n identity matrix. So that's one parameter that's involved. So now let me fix lambda, some finite lattice in d dimension for some d. And so maybe just to have a picture in mind, I'll just draw an example here so that I can refer to it later. So maybe here it's a 2D lattice. So this is lambda. And then so these lattice gauge theories turn out to be probability measures on a space of configuration sigma, which maps edges of my lattice lambda to this group G. So here this E sub lambda, I denote as the space of the edges of my lattice lambda. And so it's basically a probability measure on the space of edge configurations. And to define it, I need one last parameter beta, which is non-negative. And so given these three parameters, G, lambda, and beta, I can define this probability measure, mu lambda beta, this lattice gauge theory. And it's defined as a Radon-Nikodym derivative with respect to this base measure here, which I just take to be the product harm measure. Because you can think of this configuration space as just the product of many copies of G, one copy for each edge. So I just take product harm measure, that gives me my base measure. And then the value of this density at a given sigma is just some normalizing constant times e to the minus beta, some action of sigma. And so where I need to define this action. That's what I'll do next. So this action, usually it's called the Wilson action. And It's defined as follows. So the action of some sigma is defined as summation, well, 1/2 times the summation over plaquettes. So I'll say what plaquettes are in a moment. So this distance squared between the identity matrix and sigma p. And I'll say in a moment what sigma p is. But here I just want to give sort of the general form of what this action looks like. And yeah, so if you notice here, so this norm here, so first IN and sigma p are going to be matrices, and so this is just the usual Frobenius norm for matrices. Okay, so to complete this definition, I need to say what plaquettes are and what the sigma p is. So by plaquette, I just mean an elementary unit square of this lattice. So for example, each of these unit squares is a plaquette, so I'm summing over them. And then what is sigma p? Well, if I have a plaquette with 4 boundary edges, E1, E2, E3, and E4, I just define, so abusing notation slightly, I define sigma p to be sigma E1 times sigma E2 times sigma E3 times sigma E4. Okay, so that's a complete definition of lattice gauge theories. And maybe now I just want to pause for a moment and make some elementary considerations about the behavior of this measure. Right, so suppose we take beta to be large, well, fairly large. So what typically happens if you take a random sample from this measure? Well, you want this action to be small, because you're taking exponential minus. So you want this action to be small. And so what does it mean for a configuration to have a small action? It means that for most plaquettes in your lattice, the associated plaquette variable sigma p is close to the identity matrix. Right? And then you might ask, well, okay, so what are the minimizers of this action? Well, one obvious minimizer, if I just take the all identity configuration, so I assign every edge the identity, that means every plaquette variable will also be the identity, and that gives me 0 action. But it turns out, in fact, that this is not the only minimizer of this action. In fact, there are many, many minimizers of this action. So it sort of comes out of this thing called gauge symmetry, which also has an analog in the continuum, where actually, if I give you a lattice lambda, you're going to have exponentially many minimizers in the size of the lattice. And if you want to see an example, well, for purposes of time, I won't give an example now, but I'm happy to give one, how you construct these minimizers later on. Yeah.
So when you're talking about minimizers, does that mean global minimizers or?
I just mean, I guess global, I just mean, say, configuration sigma, which gives 0 action.
No, just really zero.
Yeah.
Really global.
Yeah.
You don't put boundary conditions.
Oh, you can. So yeah, so people, you can put boundary conditions, say Dirichlet boundary conditions or periodic or free. Yeah, so that could also go into the model. Yeah. Any other questions about the definition? Yeah, one thing I can also say, so okay, for purposes of time, I'm not saying now, but so these notions like edge configuration and this Wilson action have also natural analogs in the continuum, because indeed they were obtained as discretization. So if you're interested, I can say more at the end of this talk. Let's see. Okay, so but now I want to move on and talk a bit about some of the basic questions one can ask about lattice gauge theories, right? So I've defined this probability measure. What do we try to prove about it? And so the basic questions involve these things called Wilson loop observables. So I want to define that next. The definition is very quick, just one line. So I start with a closed loop in my lattice, gamma, say with edges E1 through En. And then I define, so given gamma and given a configuration sigma, I define this sigma gamma, again abusing notation, just to be the product of sigma E1 through sigma En. So you can think of this as you're traversing your loop, and then every edge you take, you multiply by the group element assigned to that edge. And so given all this, I can define this function W gamma on configurations, which takes sigma to trace of sigma gamma. And so this function is exactly what is known as a Wilson loop observable. And so perhaps the most basic question one can ask about a lattice gauge theory is, okay, suppose I sample a random configuration, capital sigma. So I have this configuration which is distributed according to the probability measure I just defined. Can I compute this Wilson loop expectation? Okay, so this expectation of W gamma applied to this random configuration. Okay. So can I compute it? And so it turns out, okay, in general, you cannot actually give an exact computation, right? Okay, except for in special cases, you can't have an exact formula, but for example, you can try to prove upper or lower bounds. And so it turns out it was sort of known from the beginning that if you start taking this loop gamma to infinity, you're going to fall in 2 cases. So maybe to fix again, idea, suppose I take gamma to be a rectangular loop where both sides are going off to infinity. So it's some sequence of loops. So it was sort of known that you can only fall in one of two cases. So this first case is known as the area law, where, okay, so maybe I should put absolute values here. But the absolute, where this regime is where the absolute value of this Wilson loop expectation is bounded by, it's decaying like exponential minus the area of, say, this rectangular loop, right, as the loop goes to infinity. So that's one regime that you could try to show. The other regime is where you actually have a lower bound instead, where now the Wilson loop, again with absolute values, I suppose, is not decaying too fast. So it's lower bounded by exponential minus perimeter of the loop. And of course, in general, the perimeter is much smaller than the area. So these are two very different regimes. Right? So one, you have a very small lower, or very small upper bound, and the other, you have a relatively larger lower bound. So these are sort of the two basic regimes one could try to prove that these Wilson loop observables satisfy. And so to maybe quickly survey some of the previous work on this area. So Ostermatter and Seiler proved that the area law actually holds as small beta for any group G and basically any dimension. So this was perhaps the first result. And then later on, Gofford and Mack in 1982 were actually able to show the area law in 3 dimensions for this group U1. So it's an abelian group. And then one might wonder whether the same is true for U1 in 4 dimensions. This was proven to actually be false by Guth in 1980 and Foyek and Spencer in 1982. They actually showed that you fall in this regime, this perimeter law, at least at large beta. So you have this transition for this group U1 in 4 dimensions, where at small beta, you're in the area law regime, and at large beta, you're in the perimeter law regime. Right. And okay, so that's a quick survey of some, perhaps, of the previous work about, say, upper bounding, lower bounding Wilson loop expectations. And so now in the remaining part of this talk, okay, I forgot to mention. So, okay, here's perhaps the maybe big open problem in lattice gauge theories, which is to prove the area law for 4 dimensions, but also 3 dimensions would be good for any G, which is not a non-abelian Lie group at any beta. So this is still open. And okay, there are some physical interpretations in terms of what this means for Yang-Mills theories or the physics behind it, if you manage to prove it for 4 dimensions.
Is it obvious for dimension 2? Or am I missing?
Yeah. Great point. So in 2 dimensions, I wouldn't say it's obvious, but it's no. Actually, in 2 dimensions, you can exactly give a formula for these Wilson loop expectations. Or from there, you can read off there.
You say any beta, but you have the Osterwalder-Seiler result, which already shows it at small beta?
Yeah, so you would want to show it for a large beta. Well,
any beta except for D.
Oh no, you want to show area law holds not only for small beta, but all beta. Yeah.
All beta.
Yeah.
Not any.
Yeah. Okay, so maybe now I'll quickly talk about, in the last part of my talk, some of the work I've done. And so for this, we're going to make a major mathematical simplification, which is we're going to take the group G to be finite. And so once you do this, you sort of lose all of the relevance to physics, sort of. But I would say that these finite group lattice gauge theories are interesting from the point of view of, say, the statistical mechanics, because what you get is some natural generalization or extension of the Ising model. So perhaps you have heard of the Ising model before. If not, that's perfectly fine. But just know that the Ising model is perhaps the classical model of statistical mechanics, and it's been very well studied. And so when you take this group G to be finite, you get these finite spin systems, which sort of look like an Ising model, but with some complications. And again, so you can ask the same sort of questions, like whether, okay, can I compute Wilson loop expectations if I take G to be finite? And so you can start in the simplest case, Z2, which I represent as plus or minus 1. And in this setting, Chatterjee showed that, very recently showed that at large beta, basically he was able to approximately compute these expectations, and he gave an explicit formula. So the expectation, well, Wilson loop expectation of a loop gamma is approximately e to the minus 2 times the loop length of the loop gamma times e to the minus 12 beta. So I guess the important thing is not so much a formula, but more that he was able to approximately compute these things when beta gets large. And the approximation becomes exact as beta goes to infinity.
And what dimension is that?
Yeah, great point. So you proved it in 4 dimensions, but probably the method works in any dimensions because these finite group things sort of.
Sorry, absolute gamma is length of gamma.
Yeah. So yeah, the length. And so, yeah, so the first result I wanted to talk about is, so I was able to generalize Chatterjee's result to arbitrary finite groups, where, so instead of this formula here, I gave a suitable generalization of it. So again, it's the same setting, so at large beta. I proved it in 4 dimensions, but probably the proof would work in any dimension. What else did I want to say about this?
And the distance you take on V does not matter
The distance that I take on
from the group.
the group? Oh, so what distance, you mean this, let's see.
But the analog or absolute value of trace or something like that, yes.
This one?
Yes.
Probably it does. I think if you take a different action, probably the same methods could work, but the formula itself is going to change.
And what do you use?
So the proof method is sort of, I guess, sort of like this low temperature expansion, which is often common in statistical mechanics, but there are some twists when you try to work with gauge theory. So usually these low temperature expansions, they were at least first developed for the Ising model and say Potts models, but then you could also try to use them for gauge theory. So this type of thing. And yeah, so I'm not going to give the formula because I don't know if it's that useful. And then the last results I wanted to mention is that, so this is joint this year with Arka Adhikari, who's currently a postdoc at Stanford. We showed, so in the same setting, so finite groups at large enough beta, if you have any two loops which are far apart, well, they're covariant, the covariance between the 2 Wilson loops is going to be decaying exponentially in their distance. So maybe you can interpret this statement as saying, okay, so I have this lattice model, then 2 different or 2 far apart regions of my model are essentially non-interacting because they have covariances which are exponentially decaying. So that's sort of how you can interpret it. And yeah, so that's all I wanted to say today. Thank you for listening.
So you expect there to be a phase transition in which beta goes from small to large, a single point of phase transition, or the area law changes into a perimeter law?
Yeah, so especially for abelian groups, I think one can show that this constant here, this constant is going to be probably monotone in beta. So I stated as inequalities, but you can sort of write an asymptotic here, and then this constant will be well defined, and it should be monotone in beta using just classical correlation inequalities when you have a finite abelian group, or abelian group in general. And so for that, I guess you only get a single phase transition.
And also about the last slide with the covariance, when studying the Ising model at large beta, there is a talk of 2 Gibbs measures, the plus measure, the minus measure. Is there anything like that here? The one
Yeah, I think so. There's this paper by Christian Borgs from I think 1984, where he looks at, I think, Gibbs measures which are not translation invariant. You could have multiple. Yeah. And for the Z2 gauge.
because you write covariance beta, this is in some boundary condition.
Oh, this is free boundary condition. Free.
You took R measure on all these G's. If you had taken some other continuous measure, do you expect to have qualitatively all the same phenomena?
It would not be good gauge invariant.
Like one natural, yeah. So so one natural candidate you would take instead of R some heat kernel measure. But exactly, so you would lose gauge invariance if you do that. But maybe if you take a heat kernel. Well, heat kernel is conjugacy invariant, but I don't think it's what you can get is gauge invariant even then.
Great, let's thank Scott again.